about Coulomb's inverse square law of magnetism. So, what is the force between two isolated poles? So, here, according to definition, Coulomb's inverse square law, force between two magnetic poles, maybe attraction or repulsion, is directly proportional to product of their pole strengths and inversely proportional to square of the distance between them. So here R is the distance between the poles, M1 and M2 are pole strengths. So to remove this proportionality, they use a constant mu naught by 4 pi. So we have mu naught by 4 pi value, that is 10 power minus 7 Newton per ampere square, where mu naught is permeability of free space. What is permeability means? The medium, how it allows magnetic field through it. So how easy or difficult it allows, that will be represented with mu naught here. Mu naught is permeability of free space. If the medium is other medium, we can simply represent with mu. And its value, mu naught by 4 pi is equal to 10 power minus 7. For vacuum, we can write like this, 10 power minus 7 Newton per ampere square. Dimensions ml t minus 2 a minus 2. So the force between two isolated poles, we have a formula here. This is only magnitude, but force is a vector quantity. The vector notation of the force F is equal to 1 till you can multiply with R bar and divide with R. Then what you get? R bar by R, you get unit vector along R bar we get. In definition also they mention force directly proportional to product of their pole strengths and inversely proportional to square of the distance between them, and it is acting along the line joining of the poles they mention. So that is the reason we are taking here R bar. R bar is along line joining of the two poles. So this is a vector notation of the force. From this formula you see that if F is equal to 10 power minus 7, mu naught by 4 pi also 10 power minus 7, these two get cancelled, and R is equal to 1, then M1 into M2 is equal to 1. What happens if both poles are same? M square is equal to 1, then M is equal to 1. Using that concept, we can define unit pole. What is unit pole? If the force between two poles of equal strength. So equal strength means M1 is equal to M2, which are separated by 1 meter distance. R is equal to 1. And the force is equal to 10 power minus 7 Newton. Then 10 power minus 7, this get cancelled, this become 1. M into M, M square is equal to 1. Then M is equal to 1 you get. Like that they define pole strength. So equal to 10 power minus 7 Newton, then the pole is said to be unit pole. Now we'll see force between two magnetic poles when it is placed in a medium. The force between magnetic poles when they are placed in a medium. So medium means what factor here changes? That is mu factor, that is permeability changes. Here F medium is equal to mu by 4 pi M1 M2 by R square. Mu permeability of the medium and mu naught is permeability of free space. We have some relation between these two. Mu is equal to mu R into mu naught. What is mu R? Relative permeability. So relative permeability means you see that mu is permeability and mu R is equal to permeability of the medium by permeability of free space. From this mu value we can write mu R into mu naught. So that we can substitute here, and mu naught by 4 pi M1 M2 by R square is force when two poles are placed in air or vacuum. Then we can write mu relative or mu R into F air. So what is the relation between force acting between the poles in medium to force acting between the poles in air means Fm is equal to mu R into F air. Now we will see an application on force between two magnetic poles. Here they are taking three identical magnetic poles, all are north poles only, and each strength is small m and small m, and let us consider here A, B and C points. If they want, what is the force acting on a pole which is placed at point B? You know that this north pole repel this north pole, the force is acting away like this. That will be represented like this. F is equal to mu naught by 4 pi. And what is the pole strength here and here? M1, M2, both M and M square by distance. Side of the triangle you can take it as A, equilateral triangle, and A you can take here. Similarly, what is the force acting by C on B? So it is acting like this, in this direction. So this angle is 60, so this angle also 60. One force like this, other force, one force like this, other force like this. Opposite angle will become. Then that also 60. You can extend like this. One of the force like this, other force like this. This is 60 degrees. We know two equal forces are there. Two equal forces. Angle between those two is theta. Then what is the resultant force formula? Using parallelogram law of vector addition, 2f cos theta by 2. And f value we know, mu naught by 4 pi m square by a square. And cos 60 by 2, cos 30, root 3 by 2 we get. So net force what we get? Root 3 mu naught by 4 pi into m square by a square we get. In last example, all three poles are identical. Here also identical only, but one pole here I made to south pole. Last time all three are north poles only. Now one I made different pole, unlike pole I made here. Now what is the force acting on point B? You know that this north pole repel this north pole. The force acting away from the A. And this is the south pole which is attracting the north pole. That's why it is acting towards to south pole. Parallel to this we can take force F. Magnitude same only. M, that is mu naught by 4 pi. Mu naught by 4 pi. Here F is mu naught by 4 pi m square by a square. Here also same magnitude. Why? Because pole strength is same, but only difference here it is south pole. So it attracts. So same amount of force is acting here and here. But what is angle between those two forces? That is 120. Why? Because here 60, and if you extend this line, that total is 180, and 180 minus 60, this become 120 degrees. Now what is the formula? F resultant, F net is equal to 2F cos theta by 2. 2F value we can substitute this one, and cos theta by 2, cos 120 by 2, cos 60. Cos 60 1 by 2, and substitute the value. We get F net is equal to mu naught by 4 pi m square by a square. You see that there is a force due to one of the pole only. That means if two equal vectors which are making an angle 120 between them, then resultant also equal to any one, equal to magnitude of any one vector. So this case we can take a P is equal to Q is equal to R case, then theta is equal to 120 we get. Parallelogram law of vector addition, we have this relation. Fifth case. Now you see there are four identical poles. So placed at A, B, C and D. Suppose if you want to calculate force acting due to these three poles at point C. All are identical inside is A you can take. Then what is the force between B and C? That is F is equal to mu naught by 4 pi m square by a square. Similarly from D and C also. Same value. That you can take it as F2. F1, F2 both are same distance, that's why same. But what is force acting due to A on C? That is from here to here distance is root 2A. So due to that what get F is equal to mu naught by 4 pi m square by root 2A whole square. Nothing but 2A square we get. And here we have three forces. One is F1 acting along horizontal, F2 acting vertical, and F3 acting slantwise like this, making 45 here. We know F1, F2 both are equal. So resultant of these two also acting along F3 direction only. What is the resultant of F1 and F2? That is root 2F. Two equal forces, each magnitude F, are perpendicular to each other, means what you get resultant force F resultant is root 2F we get. So here resultant force is equal to F1 plus F2 plus F3. So but F1 plus F2 is root 2F and F3 is F by 2. Why it is F by 2? You see that What is f value? Mu naught by 4 pi m square by a square, but here by 2 is there additionally, so we can write this as f by 2. Now resultant of these two is acting in this direction, that is root 2 f, and f by 2 also acting in the same direction. Both are in the same direction, so you can add directly. So root 2 f plus f by 2. So in place of f, substitute the value mu naught by 4 pi m square by a square. So force acting on one of the pole when four identical poles or pole strengths placed at four corners of a square of side A. Now we'll see about concept magnetic field concept. The space surrounding a magnet, not only magnet, any magnetic substance, a magnet in which its effect is felt is called magnetic field region, up to where the effect of magnet fall, suppose if it is attracting or repulsion takes place, the total space we can call it as a magnetic field region. And after that, magnetic induction, just like in electrostatics, electric field intensity, here in magnetism, magnetic field induction is there, which is represented here with B bar. There in electrostatics it is represented with E bar, here it is B bar. How they define B? It is the force experienced by unit north pole at a particular point. We can say field intensity at that particular point. Suppose you can take here a single pole is there and its magnetic pole strength is M, and at a particular distance R, take a point P, and here you have to assume unit north pole, and it is north pole and strength is 1 ampere meter. This is unit north pole. If you place here unit north pole, what is the force experience? That only field intensity, field induction B. So what is force? F is equal to mu naught by 4 pi m1 m2 by r square formula. But here in place of F, take B and mu naught by 4 pi. One of the pole is having strength M, other one having strength 1. So m into 1 by r square we get. So this is due to a single pole. What is magnetic field induction? That is a formula. B is equal to mu naught by 4 pi m by r square. And if you want a vector representation, multiply with r bar by r. So denominator become r cube, here r bar. R bar by r we can write as unit vector r cap. So now what is the relation between force and magnetic field induction? So how they define B? There is a force acting for unit north pole. If m is equal to 1, B is equal to F it become. What is B here? Magnetic field induction or magnetic field strength we can say. Magnetic field induction or magnetic field strength. Its units is force by pole strength. Force units are Newton. Pole strength is ampere meter. So Newton per ampere meter, or SI unit Tesla, based on scientist name they put Tesla, and you can represent with capital T also. What are the dimensions? So dimensions of force by dimensions of pole strength, that you get M L0 T minus 2 A minus 1. L terms get cancelled here. Now we'll see some applications on magnetic field induction. Three identical poles are placed at the vertices of equilateral triangle of side A. Find the magnetic field induction at the centroid of the triangle. So here I assume ABC triangle, and each corner identical pole is there, north pole and north pole and north pole. Strength also you can take M and M. What is the field induction at the centroid they want? First of all, to apply the formula, what is magnetic field induction formula? B is equal to mu naught by 4 pi m by r square. To apply this formula, we need to calculate what is the distance between the pole and the point. Suppose from C to centroid, what is the distance? This is A and this is A by 2. This is angle 60. So if you use sine 60, opposite by hypotenuse. Using that, we can calculate opposite side is root 3A by 2. This total length is root 3A by 2. and centroid divide this line to 2:1 ratio. So 2:1 ratio it divides. So then what is the distance from centroid to any one of the vertices of the triangle? That we can write like this. This is OC, this is a CD or DC. So OC is equal to 2 by 3 of CD. Because 2:1 ratio, total 3 parts, 2 parts required. And this total distance root 3 a by 2. So from that you can calculate a by root 3. Now what is field intensity or field induction due to A, B and C at this point? Means all are at the similar distance, same distance is there. So magnitude of A, B, C all are same. That is here we can calculate, that is mu naught by 4 pi m by, here what you can write, A by root 3 whole square now. A by root 3 A square by 3 we can write. So due to any one of the pole, this is the strength we get. And what we want, and B also a vector quantity, but because it is force acting on unit pole strength. So force is vector, so B also vector quantity. So you should add vector sum. Superposition of all the fields. But you get like this here, and due to B, you get field like this, B like this, and B like this, and B like this. You know that two vectors of equal magnitude B and B, and angle between those two is 120. You get same as one vector magnitude we are getting, and that will be exactly opposite to this B. That's why what happened, resultant of these two cancels this. So what is the net field acting at the centroid? That is 0 we get. Net field. Here important thing, and to calculate distance from C to O, that is a 2:1 ratio, and after that, and what is a magnetic field induction from due to C at point O, that is here to here distance is what you get, A by root 3, then mu naught by 4 pi m by A by root 3 whole square, you get 3 here in your numerator. Similar application here, last case, here north pole, here north pole, here also north pole, but now here I took here south pole. What happened? Magnetic field induction at the centroid now. Of course, strength is same only because of a similar position. So we can take the same value what we calculated earlier for each of the pole, how much field we get at the centroid. That is O, that is BA, BB and BC all are equal to B due to A, B due to B and B due to C is equal to 3 mu naught by 4 pi m by A square we get. Now we'll see about directions. Directions. See, and here due to this is a north pole, it will be repel like this. But because where we calculate field, there you have to assume unit north pole. So this north pole repel like this. So parallel to that we get a B here, and this attract because it is a south pole. Where you calculate field there, you should assume north pole now. So it will be attract. So B is acting like this parallel to this, and this north pole repel downwards. This north pole is at C, north pole is there, that repels this unit north pole downward. That's why due to that you get downside. But magnitude of field induction is same for all, B, B and B. You know that this total angle is 120. So what is the resultant of B and B? That is angle between those two 120. You get the same as one of the field. So you get B in this direction. Resultant of these two, we get B in this direction. Due to south pole, and again we have B in the same direction, both are in the same direction, then finally what you get resultant? 2B we get. Resultant of these two is B, and that is same direction as the field due to south pole. So total 2B field is acting there. Just what is the difference, what is the change in previous question here? There, here I took north pole identical, all get cancelled here. If I took one pole as a reverse, here south pole, and field become 2 times of there. So 2 times means you can write that 2 times of 3, 2 times of this value. That what you get 3 mu naught by 2 pi into m by a square. 3 mu naught by 2 pi into m by a square it become. Now another case, you can take a horseshoe magnet. So horseshoe magnet is bent. It will be like this. If the distance between these two poles, you can take it as d. What is the field induction at the center? Nothing but from here to here, distance is d by 2, and from here to here also distance is d by 2. Due to north pole, what is the field induction? V is equal to mu naught by 4 pi m by d by 2 whole square. Nothing but d square by 4, 4 is sent to numerator. That 4 get cancelled, mu naught by pi m by d square we get. And this also same distance now, so magnitude is same only, same as this. But what is the direction? Here where you need to calculate field induction, there you have to unit north pole, assume unit north pole, and this north pole repel and this south pole attract, both are in same direction. That's why I add these two fields. So B is also mu naught by pi m by d square. Add these two, 2 mu naught m by pi d square. In books they give that 8 mu naught by 4 pi m by d square they give. Put the same. Now we'll see about magnetic line of force. What is magnetic line of force means? If you release a unit north pole freely in a magnetic field, then it follows some path. The path followed by unit north pole in magnetic field, what you call magnetic line of force or magnetic flex line. And what are the properties of this magnetic flex lines? Magnetic field can be represented with the magnetic lines of force. They are imaginary. Suppose at north pole if you take, they are divergive, that is divergive, and at the south pole they are convergive. For example, you see in diagram, you see north pole, if you release a unit north pole near the north pole of the bar magnet, it is moving from north to south. So flex lines comes out of the north and enters into south. So at north pole those are divergent lines, and at south pole those are convergent lines. The magnetic lines of force never intersect. If they intersect, it means field lies in two directions and at the point which is not impossible. Suppose you can take two vectors simultaneously acting at a point. Suppose two forces acting simultaneously at a point. We get these two get cancelled and we get a resultant force between them. Similarly here also, if two magnetic lines are intersect, then by cancelling that both will be vanished and you get a resultant magnetic line we are getting, magnetic line of force we are getting. That means we didn't find two lines of force intersect. If they intersect, that only they mention here. It look like a field is in two directions, which is not possible for vectors. Inside the magnet, they are moving from south pole to north pole. Outside the magnet, from north pole to south pole. See in the diagram here. So see the diagram which is on a right side, a bar magnet, and outside you see magnetic lines are moving from north pole to south pole, and inside the bar magnet they are moving from south pole to north pole. These magnetic lines are closed loops. So that is the reason we can't split the poles. Suppose if you want to split the poles, suppose if you want to take isolated pole, if you break the magnet at the center, automatically it can induce other pole also. Reason because of this closed loopness of the magnetic line of force. Magnetic line of force always in closed loops. So they come out of the magnet at north pole, enter into south pole. Inside the magnet, they are moving from south pole to north pole. So inside the magnet they are from south pole to north pole, and outside the magnet they are from north pole to south pole. They are closed curves. The tangent at any point to the line of force is given direction of the magnetic field induction at that point. Suppose if you take near north pole, so the field is going away. Near south pole, the field is going inside. Suppose exactly between north and south pole, if you take bisector line, somewhere here, bisector line, the field lines are parallel to the magnet. You see that here at any point, what is the direction of the field means? That is the direction of how magnetic lines of force are moving. At any point, if you draw the tangent on the magnetic line of force, that gives the direction of the magnetic field. If the line of force are crowded, this means more density is there, number of lines is more, then we can say stronger field. And they are moving away, means rarer is there, rarer flex lines, less denser, then field is weak, we can say. That means, for example, you see here, and in you see that here in second diagram, and initially, and the lines are crowded. When you're moving from towards to right, the lines goes away. So field is more initially, and then after moving right side, field is less. So more here also, near north and south poles, field is more, but if you are moving away from north pole or away from south pole, field is less, because lines are moving away. Now let's see about magnetic lines of force for bar magnet, and they are moving from north to south. Inside the magnet, he didn't show here. Inside the magnet, they are moving from south to north. Suppose if you take one north pole and one south pole, unlike pole joined together, what happened? Flex lines are moving from north pole to south pole. If you bring two north poles nearer to that, the flex lines are repel each other. You find a white space here at the center. There is no flex lines. There is no magnetic flex lines. That means there is no field. No field means that is a neutral point, we can call. Between two poles, two like poles, we can get neutral point somewhere. Of course, where we get means depend upon their strengths. Suppose both have equal strength means exactly center we get. If one is stronger means it is nearer to weaker pole we get. Now what is the main difference between electric line of force and magnetic line of force? So already we know electric lines of force started at positive, ends at negative. These are not closed curves. They have starting and ending point. But magnetic lines of force not like that. These are closed loops. Outside they are moving from north to south. Inside they are moving south to north. And magnetic lines of force passes through the substance, but electric lines of force not passes through the conductor. In electrostatics, we have this concept. If you take a copper sphere and electric lines are not passing through the copper for good conductor. But here, if you take a bar magnet and magnetic lines are easily passes through the iron. So that is the main difference. It can passes through the conductors, magnetic field, but electric field is not able to pass through the conductors. And other point, one is closed loops, that is magnetic field are closed loops, and electric lines are not closed loops. They have starting and ending points. Now we'll see about uniform and non-uniform fields. What is uniform field? In a region at any point, if the field strength is same, that means if you release unit north pole in that space, everywhere it experiences same force, we can say that is uniform field. Otherwise, by using magnetic lines of force also we can define. If magnetic lines of force are parallel and equidistant, like this. You see uniform field, parallel and equidistance. This is representing uniform field. Suppose what is a non-uniform field, and at different points different field intensities is there, magnetic field intensities are different, then we can say non-uniform magnetic field. That means if release unit north pole in that space, at different points it will experience different forces. Example you see on right side diagram, and initially crowded lines and they are moving towards to right, the lines are moving away, field is decreasing here. That is non-uniform field. All the examples, all the cases what we observe here, this is also non-uniform field, and due to bar magnet and due to two like poles also non-uniform field, and due to like poles also non-uniform field we get. But we can consider, you see, in case of Earth's magnetic field, suppose if you take Earth, we can consider as a bar magnet. Earth we can consider as a bar magnet, and due to Earth's magnetic field flex lines we are getting like this. So it is a huge magnet. It is a huge magnet means you can say, suppose if you go to very narrow point, here you see almost parallel lines we are getting. Almost parallel lines. So it is, Earth's magnetic field is not uniform field, but in a given region, huge magnet in a given region, if the distance is not changing that much means we can consider that as uniform field. So that only what we call Earth's magnetic field. So here they give comparison between Earth's magnetic field and a bar magnetic field. Both are similar. But here they give two axes. One is axis of spinning. Other one is a magnetic meridian direction. That is a blue color line shows the line joining of north and south magnetic poles of Earth. And a spinning axis shows that the line joining of north and south, of geometric north and south of Earth. Another example to get a uniform field is, and if you take horseshoe magnet, between the poles if you observe almost parallel lines we are getting. At the edges means magnetic field little shows non-uniform field only, but exactly between north and south poles means it shows uniform field, parallel lines and equidistance. This is an example for uniform field. That is the reason whenever they required uniform field, they use horseshoe magnet. And based on Coulomb's force, problems are there from 14 to 19, and magnetic field induction problems are there